Hello everybody and welcome to unit 2 of the course on Introduction to Programming in C. What we are going to be looking at in this set of videos is the problem of data representation. Right? In particular, when we work with a computer, one of the things that we assume is that the computers are processing data, right? Processing meaning that maybe they are performing computations, maybe they are working with text, whatever it is. There is something that is required as a fundamental step over there, which is how do we get the data into the computer in the first place, right? And we now have a rough idea of how a CPU works, right? There is an arithmetic and logic unit, there are some registers for temporary storage of information, and there is memory which actually stores the data that you are working with. What we are going to be looking at over here is how should that data be represented in such a way that a computer can make use of it. So the outline of this set of lectures is roughly going to be along the following lines, right? The first thing that we are going to look at is how do we represent data inside a computer, right? We will then get into another section which is on instructions, because it turns out that instructions can also be encoded as some kind of numbers, which means that we can use a very similar kind of representation what we do for data in order to store instructions as well. That naturally takes us to the next stage, which is what does it mean to compile a program? In other words, when we write a program in a high level language like C, right, and C compared to assembly at least is a high level language, how do we then go about generating the machine code that actually needs to sit in the memory of the computer and get executed? And finally, we will also look briefly at the role of an operating system, right? Now, a word of caution over here, many of these topics are entire courses in themselves. So for example, if you get into the problem of instruction encoding, you could pretty much get into how instruction set architectures need to be designed, and that would in turn lead into an entire course on computer architecture, right? Compilers, once you start looking at how does a compiler work, how does it go about taking the input of a program and converting it into the machine code, and more importantly, once you start looking at the kind of optimizations or improvements that it can make in the process of generating that machine code, that's another course in itself, right? And similarly, of course, operating systems are at the very least one full course on them on their own, right? So naturally, what that means is that the level at which I'm going to be addressing them in these videos is going to be at a somewhat superficial level. It's enough to sort of give you a flavor for what lies underneath these topics, right? And hopefully will also ignite some interest in terms of learning more about them. Unfortunately, learning more about them is pretty much beyond the scope of this course, right? So it's not really too much that we can do over here. What I am going to be sort of trying and doing as we go through even the data representation is to focus on parts where we basically say, okay, these are things that are essential for you to know as a programmer working with a language like C. And beyond that, if you want to dig deeper into the subject, yes, there are ways that you can go further and learn more about it, but many of those topics happen to be beyond the scope of what you need for an introductory course in C. Alright, so let's start by trying to understand what we mean by data and what exactly it is that we are trying to represent over here, right? There's an interesting quotation from Leopold Kronecker, right? Some of you may have heard of the Kronecker delta function, which is something that comes up in advanced math. The quote essentially says, God made the integers, all else is the work of man. And partly the reason why that comes up is that integers or counting is something that comes naturally, right? It is something very fundamental. If at all you want to even keep track of, let's say, how many pets you have or how many cattle you have as a farmer, you need to be able to count. But anything beyond that, which starts getting into fractions, real numbers, more complicated representations, complex numbers of course, are pretty much things that come out only when you start digging deeper and deeper into trying to find out about mathematics. Now of course this statement is an exaggeration. It's not that man just created all of these things. These are things which help us to understand nature. Now why is all of this relevant? Because we use computers in order to enhance our understanding of nature, right? We want to be able to solve problems, And for that we need to have ways of representing all the different kinds of numbers and techniques and data in general, right, that we have to deal with. So the first question of course is, why do we need to look into this problem of data representation, right? And even by just looking at these slides, one thing should pop up, fairly obviously, which is humans use a variety of symbols, right? Now I have written out these symbols in this case by hand, right? But you could have typed them out, right? Or you could have had a computer generate something in what looks like a good handwriting, right? Any different ways are possible of generating symbols. The point is that humans are very good at recognizing symbols, which means that we can use a very large number of symbols in order to represent the different kinds of values that we are interested in. Computers, on the other hand, must build everything out of just two basic data points, right, 0 and 1, right. So when people say that everything inside a computer is just zeros and ones, it's a bit of an exaggeration, right? That's not really a helpful or meaningful statement. But on the other hand, at a very fundamental level, it's also true, because the only sort of states that can be represented within a computer are 0 and 1. What the computer does with those is that by grouping them together appropriately and by interpreting them appropriately, we are able to do a lot more with those values. So as an example, let's look at this memory map that we had in the earlier discussion on the quadratic equation solver, where essentially what we said was, we assumed that the three inputs ax square plus bx plus c, the a, b and c are the inputs to our solver and they are numbers, right? And I'm going to store them in three memory locations that I have labeled 0, 1 and 2. So far so good, right? The idea of a memory location with a label or an address attached to it was, I think, well motivated, and we kind of understand why we need something like that, right? We need to be able to put something in a place and then get it back later when we would like to use it. Now, the question that was not answered at that point, or rather was not even raised at that point, was what are these a, b and c, right? We said numbers, fine, but I can't actually write a number into a memory location. I need to convert it into some form of zeros and ones. That is the first step towards understanding why there is a problem with data representation. Okay, there are a few questions we need to answer before we get into even the different ways by which a, b and c can be represented as numbers. The first thing is, can a, b and c be any arbitrary numbers, right? What do I mean by that? Well, obviously when I say a is a number, you can imagine that 1, 2, 3, 4, yes, certainly numbers. Okay, what about -1, right? Is a negative number allowed to be used for a? In this context, of course, we would naturally say yes, right? But at least for a person who is starting out from just counting, it is not really obvious that negative numbers matter, right? In the case of a quadratic equation, of course that matters, but not for a person who is just starting out counting. The next question comes, what about 3.14, right? In other words, we know that we have decimal values, right? We understand what 3.14 means. It's a decimal value. It is actually some kind of a fraction between 3 and 4, right? But on the other hand is represented using the decimal notation. Should I be able to have a equal to 3.14, right? What about 3.14 plus 2i, right, where I is basically the complex unit, right, which basically says that 3.14 plus 2i would be a complex number which has a real part and an imaginary part. Should I be able to use arbitrary complex values for a, right? The quadratic equation solver in general works for all of these conditions, right? It doesn't really care what kind of number you use, and that equation is a very general equation. But the kind of constraints that we put on a, b and c will affect how we build a computer to solve the problem. Okay. The next question that we need to sort of address over here is, how are these numbers a, b and c stored in memory, right? Clearly I've been talking about zeros and ones. We need to have some idea of how they will actually get stored. And another interesting question that comes out, which is not very obvious until you start actually looking at the zeros and ones inside the memory of a computer, is how do I know when a number starts and when it stops? because after all, inside the memory of a computer, I don't have a space, I don't have punctuation, I don't have anything to break the memory into different parts. So how do I recognize that this corresponds to a number, this corresponds to a punctuation mark, this corresponds to something else? All of those are interesting questions that we do need to address. So let's look into the problem of numbers to start with. Okay, as an example, I'm going to continue with the quadratic equation solver. Of course, I'm not actually going to go and find the solutions, because that would probably end up, for most certainly it would bring in negative numbers, it might possibly also bring in complex numbers, right, and possibly also decimal values, right. So right now I don't want to get into that, so I'm just going to leave that out. All I'm saying is, okay, if A is equal to 5, B is equal to 27 and C is equal to 956, how do I even represent these values inside the memory of a computer? So let's first look at the decimal numbers, right. I mean 5, 27 and 956, we understand them because we are used to the decimal system of representing numbers, and what that means is there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, 5 is one of those digits. In this case, I know when I say A is equal to 5, what I actually mean is that 5 is in the so-called units place, which effectively means that it has a value of 5 into 10 to the power of 0, right, 5 units, 5 ones. 27 on the other hand is a slightly more complicated number, right. It has 2 digits over there. The first, or rather the rightmost digit, corresponds to what we call the units place or the ones place, and what we are saying over here is that effectively this means that the units place 10 power 0, 7 is multiplied by 10 power 0, and in the tens place I have 2, right. So the tens place corresponds to the factor 10 power 1. I multiply that by the digit that's over there, which is 2, so I get 2 into 10 power 1. So 2 into 10 to the power of 1 is 20, plus 7 gives me 27. Right? That is how I am interpreting these numbers. Of course, by now we have been using these numbers for so long that we no longer think explicitly about the place values, right? But it's good to sort of recollect that in order to understand how we are going to do the same thing with computers. So taking the same thing one step forward, I would say that 956 has 6 in the ones place, so 6 units, 5 tens and 9 hundreds. Okay, so 9 into 10 power 2, 900, plus 5 into 10 power 1, 50, plus 6 into 10 power 0, 6, 956. So this is the natural sort of place value system that we use in order to represent numbers that we are all familiar with right from the start of school. Okay, how is that relevant to what we would like to do inside a computer? So the assumptions that we implicitly make when we write down numbers like 5, 27, 956 and so on, let's just examine those, because that will help us to sort of move forward from here. The first thing we assume is that we have a few symbols 0, 1, 2 up to 9, which we call the digits, right, and we assume that these are available to us. Now how do I know when a number starts and when it stops? The moment I start seeing digits, I sort of say, hey, this is the start of a number. But then I know that if there is some kind of a space or some other kind of punctuation, right, maybe a comma or parenthesis or maybe some other kind of symbol, right, which sort of separates two numbers, I can sort of say that, hey, this looks like these are two different numbers. Of course, you have to be a little bit careful, because we do also tend to use commas and decimal points and sometimes even underscores in the middle of numbers. Okay. Now, right now I am going to ignore that. I am going to assume that we have some way to distinguish when one number stops and another number starts. And most of the time it is obvious to us from the context in which we are looking at those numbers. The point is, all of these are human recognizable symbols. They are not 0 or 1, which after all is the only thing that a computer can understand. Now, if you are restricted to the symbols 0 and 1, right, and let's say that you end up with some kind of a long string of zeros and ones like this, and if I just put this set of values in front of you and ask you, hey, what is this, right? Is this a number? Does it correspond to punctuation? Is there some indication of a space or a break somewhere in the middle of those numbers? If it is a number, how big is the number? What is the value of the number, right? All of those are questions that I can naturally ask if I am just presented with this value out here, right? And in general, there is no way to know whether do these 4 symbols correspond to a number? Do these 4 correspond to punctuation? Does the entire thing correspond to a number? Does this part correspond to, let's say, an encoding of some character? Does this correspond to a question mark? We don't know, right? And it's impossible to know in general. And what happens is that the only real solution for it is to use conventions. Okay, what do we mean by conventions? I will be talking more about these as we go along, but the basic idea is that at some point you should be able to look at a set of values somewhere and say, given the context, right, this is where I see these values, this is where they start, this is where they stop, this is how I should interpret them. Okay, because you know that context and you know that this is how you should interpret them in the context, you are able to make sense of those values, right? If on the other hand these numbers were just sort of stored, they were fossilized and seen by whatever humans have evolved into a million years from now, a human looking at, or a creature looking at it at that point will just see a string of zeros and ones and does not have context, cannot make out whether this corresponded to a number, a symbol, or anything else. So that context, right, what is it that you are trying to represent is important, and pretty much everything that computers do and how we make use of them relies on the fact that we can understand the context in which we are looking at a number or a value and make sense of it in that way, right? So please keep this in mind. There are a number of places where I will say this is how an integer is represented or this is how a character is represented, and it's important to remember that those are conventions. What that means in particular is it is entirely possible that someone else could come up with a different set of conventions, right? And effectively what would happen at that point is what you have written down will mean something different to them, and what they have tried to put down will mean something different to you, or more likely will not mean anything useful. Okay, the reason why conventions become important is so that we can communicate from one person to another. If 2 people decide that apple means different things, right, then it's impossible to have a conversation about eating a kind of fruit, right? But on the other hand, as long as people have a certain image that comes into their mind when they hear the word apple, of course in this case that could be confusing because you might end up thinking of a laptop or an iPad or an iPhone. Hopefully you think of a fruit instead, right? As long as that happens, yes, the conversation makes sense. So if someone says I ate an apple yesterday, you know what they are talking about because the word apple has a certain visualization, a certain meaning that comes into your mind when you hear it. And in the context saying I ate an apple, you are reasonably clear that this must refer to the fruit. Okay. Now in the same way, what computers do is they rely on conventions. I have a certain amount of memory where I can store these symbols 0 and 1, okay, and depending on where in the memory they are stored, what is there before them, after them, and so on, I will interpret them appropriately. So let's get into a little bit of detail on how numbers in particular could be represented using this binary system. And why am I saying binary? Because I have only 2 symbols out here, 0 and 1, right? So anything which works with 2 symbols can be referred to as a binary system by basically the prefix for the number 2, right? If it had 3 symbols, it would be called ternary. If it was 4, it would be quaternary. Decimal basically refers to the fact that there are 10 symbols, right? For the digits at least. We don't have a similar thing for the alphabets and so on, but we are talking about numbers out here. So if I have only 0 and 1, the question then becomes, how can I, for example, go about representing a number like 5? Now when I say 5, obviously I mean the decimal number 5, right? Because in binary there is only 0 and 1, there is no 5 as such. What can I say 5 is equal to? I can sort of break it up and say that 5 is actually equal to 4 plus 1, right? And the reason I've written it as 4 plus 0 plus 1 is that once again I'm trying to translate this into a place value kind of a system, right? I basically say, okay, I have 2 to the power of 2, 2 to the power of 1, 2 to the power of 0, right? Ideally, I should be starting from the right side so that I know exactly when to stop, right? I start 2 power 0, 2 power 1, 2 power 2, 2 power 3. The point is, I don't need to go as far as 2 power 3 because that is 8th, which is already greater than this number that I am trying to represent. So I know that I can stop at 2 power 2, and if I try breaking this up, it basically looks like 2 power 0 plus nothing out here in the sort of 2's place, right? I don't want to call it the 10's place, it's the 2's place over here. And this, well, we again can't call it the 100's place, maybe we should just call it the 2 power 2 place, okay? So 2 power 0 and 2 power 2 have to be added together. How do I indicate that? I put a 1 in that location, because after all I have only these two symbols, 0 and 1, right? If I put a 1 over there, it means yes, I need to add that 2 power 2. If I put a 0, it means skip this 2 power 1, and if I put another 1 over here, it means add the 2 power 0, which finally gives us this value 101 as a binary notation for the decimal value 5. Okay. This is some notation that we'll be seeing quite a lot of as we move forward, right? Which is usually that we say that we put the number 5 within parentheses and just put this subscript out here, this value at the bottom right. When I put the number 10, essentially what I mean is that this is the number 5 in decimal, that is the base that I am using in order to do this representation is 10, meaning that everything is in 10 power 0, 10 power 1, 10 power 2, right? The units place, the tens place, the hundreds place, and so on. Similarly, when I give the subscript 2 out here, it means that the number is binary, right? And when I say base 2, it basically means that this is now 2 power 0, this is 2 power 1, this is 2 power 2, and so on, right? This notation is important because remember that 101 could also have been a decimal number which has the value 101, right? So unless I explicitly put in something to indicate what that number is, it can be confusing. Now 5 on the other hand is very clear, it cannot be a binary number, right? But 101 could be a decimal number. So you have to be a little careful and make sure that you put the right notation to indicate what it is. Once again, this is part of convention, right? Now 5 was easy, right? What about 27, right? Now once again I am going to skip the decimal representation part and straight away go for place values in the base 2, right? And I am going to say I am interested in these values 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. Now you might ask the question, why did I stop there? Why did I stop at 2 power 4, right? And the reason is I actually want to find which is the largest power of 2 that is less than this number that I am trying to represent, right? And it turns out that 2 power 4 is equal to 16, which is less than 27. But if I go to 2 power 5, I go to 32, which is greater than 27, right? Just like when I know that, let's say my number is 27, do I need to have anything in the hundreds place? No, because I know that 100 is already greater than the number that I am trying to represent. So in the same way, 2 power 5 is greater than the number that I am trying to represent. So I know that the coefficient, right, that value that is going to be there multiplying the 2 power 5 is essentially going to be 0 for sure, okay. By the way, as a word of notation, these values 1, 0, 1 and so on are usually referred to as bits, right, where bit is essentially a short form for binary digit, okay. So I will be using the term bits whenever we are talking about binary numbers, right. So please again keep that in mind. When I say 101, only if I have also confirmed that it is in binary, then it makes sense to call these bits, otherwise they are actually digits. So 27 I know is greater than 16 but less than 32, so I only need to go up to 2 power 4, okay. And in fact I can pretty much clearly see that this coefficient of 2 power 4, the bit value over here must probably be a 1, not probably, must be a 1, right, otherwise I am not going to get something adding up to the value that I want. Okay. Is it possible to have some kind of a notation where, even if I skip this, is there another way by which, I could have represented the same thing? Not in the normal binary notation. You can actually prove that, the representation of any number in binary using place values is unique, right? But I'm going to skip over that for now. I'm not going to try and prove it out here. The important point is, as soon as we know this value that, the number lies between 16 and 32, I know that I must have a 1 over here. Okay. So let's put that in, right, and proceed. What else do we need to do after that? I've already got a 16 and I need to add something else to get the remaining part of the number, right? What's the remaining part of the number? I subtract 16 from 27 and I get 11. So in other words, these 4 bits out here now need to represent the value 11, okay, because this one has already taken care of the first 16. Okay, so let's proceed. 11 happens to be greater than 2 to the power of 3, right, and less than 2 to the power of 4, right, it lies between those two. So I know that this value, this bit over here must be 1. Good, let's do that, right. I subtract it out and I take the remaining number, which is 11 minus 8 is equal to 3, right. Now here's something a little bit interesting. What were we checking for? When 11 was greater than or equal to 2 power 3, I put a 1 out here. But now in this case, I'm finding that 3 is less than 2 power 2, right? Because that's the next location that I'm looking at, right? 2 power 2. So when I look at 3 and I look at 2 power 2, I find that it's less. If I were to add 2 power 2, I would overshoot. I would have too big a number for what I'm trying to represent, okay? So I need to put a 0 in here, right? But it also happens to be greater than 2 power 1, okay? So that's good, it means that I need to put a 1 in the 2 power 1 place. And finally, subtract that out. 3 minus 2 power 1 is equal to 1. That is greater than or equal to, in fact it is equal to 2 power 0. So my 0's place, or rather the 2 power 0 place, also has a 1 in it, okay. So the way that I can represent 27 is, I'll add up the corresponding values, the powers of 2, right, only the ones that are needed in order to add up to 27, okay. In fact, what we can see is it basically 16 plus 8 plus, I skip this one, and 2 and 1, and when I add all of these I get 27 as hoped for, okay. Now one important observation at this point is that what would have happened if I put another 0 out in front over here, right, or another one in 0, right, keep adding zeros in front of the 16, right. So in other words, apart from the 0, if I had 0 into 2 power 5, that is 32, plus 0 into 2 power 6, plus 0 into 2 power 7, plus 0 into 2 power 8, it doesn't change the value, right. Leading zeros don't change the value of the number. So this 0 0 0, as many as I want, followed by 1 1 0 1 1, is still the number 27, okay. This is a useful observation. We will be making use of it later when we talk about negative numbers, right. It's obvious, right, it's just like in decimal, we say that 9 and 09 and 009 are all the same. We almost never write it as 09 or 009, but we know that if you put a 0 in front of it, it doesn't change the value of the number. That's exactly what we are saying here as well. So what that in turn means is, if I ask you the question, what is the minimum number of bits required to represent the number 27? The answer is 5, because I know that 27 happens to be greater than 2 power 4 but less than 2 power 5, which means that I need only at most these 5 bits and I'm done. I have a representation of 27, right. Later on we will see why this could potentially be a problem if I try representing it using just 5 bits, but the fact of the matter is, it's good enough. I have an answer out here, okay. What if I change the question and ask you, what is the maximum number of bits required to represent 27? Well, the answer is, there is no answer actually, right, because as you can see over here, I can keep adding zeros in front and make the number bigger, right? But they are not changing the value of the number, they are just changing how many bits are being used in order to represent it. What this means is I can represent 27 as a 5-bit number, I could represent it as an 8-bit number, a 10-bit number, a 20-bit number, a 64-bit number, right? Any of those would ultimately, I just apply the place value system, find out what the value is. If it's equal to 27, yes, this number represents 27 using the binary number system. Okay. Right, one more number, right, 956. Now, how would I go about doing this? I am not going to work through each and every step. I am sort of going to jump ahead and say, okay, this is what the answer looks like. I can straight away, break this down and say that 956 is greater than 2 power 9, which is 512, and less than 2 power 10, which is 1024. So, 2 power 9 is required. Okay. Then what do? I take 956 minus 2 power 9, 956 minus 512. I get that value, I compare it with 2 power 8. It turns out that that result is greater than 2 power 8. So, that bit also needs to be set. The remainder after that is greater than 2 power 7, but the remainder after that is not greater than 2 power 6, right? And I would encourage you to work through this, keep doing the subtraction business, which incidentally is exactly the procedure that is normally used when we try to convert decimal numbers to binary, right? We sort of talk about it as a division, but if you think about it, it's basically just subtracting out the powers of 2 that you want, right? The division would be sort of approaching it from the opposite direction. This is one way by which I can approach it from the larger side of things. I basically look for, do I need a coefficient of 512 to be 1 or 0? In this case, I can say it has to be 1. I can also say that the coefficient of 1024 must be 0 because that would be greater than what I am trying to represent. So, when I go through this step and keep on subtracting out and finding the remainder, at this point I find that, hey, this the remainder that I have got is less than 64, which is 2 power 6. So, skip that bit. But then I find that 2 power 5, 2 power 4, 2 power 3, 2 power 2 are all required. Once I hit this point, I actually find that I am done. I already have a representation for 956. Okay. So, 2 power 1 and 2 power 0 are not required. What does that mean? They will be zeros in the corresponding representation. So, let us write that out. I basically say that I have a 1 here, 1 here, 1 here, a 0 here, again 1, 1, 1, 1 and 2 zeros corresponding to these missing 2 power 1 and 2 power 0. This, in other words, is the binary representation of 956, right? How many bits did I need? 10, right? And how do I get that? 956 happens to be greater than 2 power 9 but less than 2 power 10, and any number in that range essentially requires 10 bits to be represented. Now, previously we saw that 27 required 5 bits and was 11011. 5 on the other hand was just 3 bits, 101. Okay. So, what should I do? Can I say that 5 will be represented with 3 bits, 27 will be represented with 5 bits, 956 with 10 bits, and how am I going to recognize them? Because they all look the same, they look like zeros and ones, right? If I just put them down next to each other, I wouldn't know where one number was starting and the other number was ending, right? So, the question then becomes, the sort of natural and obvious solution to this is, hey, use the same number of bits for all of them. Right? That way, at least when I look at the thing, I can say that if I know that a number starts here, I know where it ends because I have already been told how many bits are required to store one number, and I can assume that maybe the next number starts immediately after this one, which means that I can now start interpreting the bits that I see in front of me. Okay, and the problem is, if we ask that question, how many bits do we need? Right? There is no unique answer to that, and the reason for that is obvious, right? Like I said, I can add zeros in front over here, or for that matter even here, without changing any of these values. Okay. So, we make our choice based on other deciding factors. So, what are these other deciding factors? We'll have to sort of look at what are the other possibilities that can come in over there, right? So the other deciding factors are going to be things that actually are related to our physical constraints. We have a computer that we are designing, it has a CPU, an ALU which can perform certain kinds of additions and so on. It has memory, registers, right, that can store values, and memory that can actually store the values from which I need to fetch data. Okay, all of those are going to be parts of my decision making process. Now, one more word about binary numbers, right? If we just look at what we can do with, for example, 8-bit values, right? The numbers would start like this, right? It would be 0, 0, 0, all zeros essentially, right? Now, if I talked about decimal, I would not normally write numbers. If I asked you how many 3-digit numbers exist, you would not normally start by writing 0, 0, 0. Okay, you don't consider 0, 0, 0 to be a 3-digit number. You just say that it's 0, right? And you would say that the first 3-digit number is actually 100, right, where there is something other than 0 in the hundreds place. In binary, we don't exactly work that way. We just say if it's an 8-bit number, even if there were leading zeros, I still consider it an 8-bit number and I have to write all the 8 bits. Okay, so an 8-bit number of 0, the representation for 0 as an 8-bit number is all the bits are 0. If the first 7 bits starting from the left are 0 and the bottom bit is a 1, then I call that I say that that's 1. If I have 0, 0, 0, 0, 0, 0, 1, 0, then this corresponds to the 2 power 1 place, right? And that's basically the total value, decimal value is 2. I go all the way down, this would be equal to 255. Right, you can work that out. You can basically see it is 128 plus 64 plus etc. Finally, I'll get 255. Okay. The interesting thing is 2 to the power of 8 is 256. So it turns out that when you have added all of these things together, what you get is 255, which is 2 to the power of 8 minus 1. Right. And what that means is when I get all of these ones out here and I add 1 to it, I'll basically get the zeros all over here and a 1 in the most significant place, right? Another way of looking at this, in other words, would be that if I was to add 1 to this, I would end up getting 0, right? How we do addition is exactly the same way that we would do it in decimal numbers, right? Except that we carry whenever you have 1 plus 1, okay? I'm not going to go into the details of how we do arithmetic because we assume that the computer is already doing it for us, right? In a course on digital systems, you will actually sort of look into that in a lot more detail. So I'm going to skip over that over here. What does end up happening is that I'll get a number that looks like this, which is basically 256 decimal, right? So this is just an observation. One other piece of notation which I had not mentioned so far is that this bit is usually called the most significant bit or the MSB, and the one out here is usually called the least significant bit or the LSB. Okay, so that's just notation which, or rather terminology that we tend to use when we are talking about such values. Okay, in general what we have over here of course is that an n-bit value can take decimal values all the way from 0 up to, in this case, 2 to the power of n minus 1, 2 power n being 2 power 8 or 256 minus 1, which is 255. That's always true, right? If I had something else which was, let's say, a 16-bit number, I would go from 0 up to 2 power 16 minus 1. So now let's look more closely at what are these other factors that we talked about, right? The fact that I have a CPU, the CPU has registers inside it, and that those registers are in turn going to be getting data from some external memory, right? All of these things are going to be built up out of physical circuits, which means that they occupy space, they have a cost associated with them, they consume power. ultimately what it means is that there are reasons why I might need to restrict the size of each of these memory registers and the CPU itself, right? I can't use an infinite number of bits over there. I need to make a call at some point. The second thing, as we saw, was a uniform size for all numbers is preferable, right? If I say that all numbers are going to be 8 bits, yeah, I can only represent numbers from 0 up to 255, but at least I can look at an 8-bit value and straight away say, hey, this could be the start and end of a number. And the other thing, like I said, is you have these registers inside the CPU. Those are in turn feeding into the arithmetic and logic unit, right? And the larger those registers, the slower the circuitry is going to become, right? The reason for that is not entirely obvious. Intuitively you can sort of understand, right? Larger circuits are probably going to be slower. They sort of more work needs to be done. The exact details of why they are slower, you probably need to go into a course on digital systems. In fact, a slightly more advanced course on how they are implemented in order to understand exactly what the implications are. But at an intuitive level, it is obvious that larger is likely to mean slower, okay? And that is in fact what happens. And once we take all of these things into account, the fact that we have physical circuits, we would like to have uniform sizes for the numbers, and that there are all these registers that need to be implemented and in turn are feeding into the ALU, we come across this, what is called a trade-off, right? And in engineering, a trade-off basically happens when you have to make a choice. There are two possible solutions or two or more possible solutions, each of which has its own merits and demerits, right? So having just 8 bits probably means that your CPU is going to be small and fast, but it also means you have only a few numbers that you can represent. Having 32 bits means that your CPU can represent a lot more numbers, up to at least 10 power 9 or so, but is going to be slower than an 8-bit CPU. What about having 1024 bits, right? Now that will probably be very good from the point of view of the range of values of numbers that you can represent, but is going to occupy an awful lot of space for normal numbers, which are probably in the smaller range, and is going to be slow. So each of these has pros and cons, and engineering is all about making the right kind of trade-offs. At some level you have to make a choice and say, this is why I made the choice, there are these benefits, there are these drawbacks. Overall, I think this is a good reason to make a choice in a certain way, okay? Now, you might be wondering at this point, why is all of this relevant to you? Because you are only interested in learning about C programming, right? But the way that I am looking at this is, you are interested in this course because you are not just interested in C programming by itself, you are presumably interested in understanding C because it helps you to understand a little bit more about how a computer works, and possibly because you might also want to implement custom embedded type of systems, right, where C gives you the most control over what actually happens in the hardware, right? And once you take that into account, all these discussions that we had, how do we represent numbers, how do we decide the number of bits and so on, they have a direct impact on the programming language, right? In particular, we need some kind of a primitive data type, some kind of a way of representing numbers, right, that is going to be portable, meaning that once I represent it in a particular system, right, if somebody goes and builds another new processor or a new computer, I don't want to have to change all my definitions, everything from scratch. I should be able to still say, hey, this is what I mean by a number. I don't care whether you use processor from company A or from company B. They should both be able to interpret a number the same way, right? And that in fact is one of the key things, right, that the reasons for going towards a higher level language like C, right? And when I say higher level language, obviously I mean compared to assembly language and machine code, because arguably C is not a very high level language. It's not one of those things where you can express great abstractions. But when you look at it from the point of view of the hardware, it's a tremendous advancement, right? You are no longer tied to the individual sizes and numbers of each register. You can just assume that there is a primitive data type, right, which in the case of C is usually defined as the integer, right? And modern variants of C basically assume that an integer is 32 bits wide. Why do I say modern variants? Because it was not always the case, right? There were scenarios where you had 16-bit integers, right? In fact, the C language reference is sort of vague on this point. You could potentially even have a larger integer if you go towards processors with bigger registers, right? So, like I said, this is part of convention. The place where it is a big win is that it says that as far as the C language is concerned, there is some kind of standardization which tells us that this is what a number is going to be like. Unfortunately, that's also not a very solid standardization, right? It is slightly vague, and that's partly to do with how the C reference itself has been written. There are other languages that are a lot more strict in this regard, and within C itself there are other kinds of data types which we will see later, where you can precisely specify how many bits you are interested in. Okay, the important point is the language allows you to do something like that, and why that is crucial is once you are able to do something of that sort, you can then write a program, get it working on one particular CPU, one particular machine, and there is a very good chance that if somebody creates another new machine somewhere else, whatever program you wrote in C will most likely compile and run correctly on that as well. Okay, so that is sort of the important point, the reason why we go for a language like C. The impact of all this discussion that we had in terms of number representations is that it affects how the language itself is designed.